Every morning, researchers around the world log into NASA's Mikulski Archive for Space Telescopes, searching through humanity's most profound cosmic discoveries. For decades, this digital repository has housed images of galaxies forming in the cosmic dawn, spectra revealing the chemical fingerprints of distant worlds, and measurements that have rewritten our understanding of the universe. But what happens when the archive contains something that challenges our assumptions about how space agencies handle extraordinary discoveries? What if the most significant observation ever made was hiding in plain sight, labelled as routine data? This question became urgent in early 2024, when the astronomical community encountered something unprecedented in the archived observations of 3A Atlas, the second confirmed interstellar visitor to our solar system. The story begins with the Asteroid Terrestrial Impact Last Alert System in Hawaii, which first detected this object in January 2024. The designation follows the International Astronomical Union's naming convention. 3I indicates the third interstellar object ever discovered, while ATLAS refers to the detection system that found it. Initially, the visitor appeared unremarkable, a chunk of rock and ice roughly 200 meters across, following the kind of hyperbolic trajectory that carries objects between star systems. Its orbital parameters showed a hyperbolic excess velocity of 41.6 kilometers per second and an inclination of 95.3 degrees, consistent with an origin outside our solar system. Standard procedure for such discoveries involves immediate follow-up observations using NASA's most advanced instruments. The James Webb Space Telescope, positioned at the second Lagrange point, 1.5 million kilometers from Earth, represents humanity's most sophisticated tool for analyzing distant objects. Here's where the story takes an intriguing turn. Freedom of Information Act requests regularly seek access to James Webb Space Telescope observations for academic research. These requests typically return dozens of properly catalogued files, all following NASA's standard naming conventions and processing protocols. The data flows through established pipelines. Level 0 raw detector data gets processed through multiple calibration stages, producing the refined images that astronomers use for research. But in March 2024, something unusual appeared in the metadata of JWST observations targeting this interstellar visitor. The archived observation showed a timestamp of March 17, 2024, at 14 hours, 23 minutes, 7 seconds, Coordinated Universal Time. The target coordinates placed the object at right ascension 2 hours, 14 minutes, 36 seconds, and declination plus 13 degrees, 9 minutes, 42 seconds. The observational parameters were standard, near-infrared camera observations in the 2 to 5 micrometer wavelength range. What wasn't standard was the file designation and size. A typical JWST observation of a small solar system object generates files between 50 and 200 megabytes. This particular observation was listed at 1.7 gigabytes. More puzzling still, the processing level showed Level 0 raw retention override. NASA's standard protocol processes raw Level 0 data through automated calibration pipelines, then archives the raw files for only 90 days before deletion to conserve storage space. But someone had flagged this specific Level 0 file with a retention override, a designation that preserves unprocessed data indefinitely. Why would anyone need to preserve the raw, unprocessed detector data from what appeared to be a routine observation of an interstellar rock? The archived data contained 1,247 individual frames, captured over 6 hours and 31 minutes. Frame-by-frame analysis reveals the interstellar object as a point of light moving against background stars, exactly what you'd expect from something tumbling through space. But here's where scientific curiosity encounters something unexpected. When independent researchers began analyzing the raw detector outputs, they discovered spectral characteristics that didn't match standard models for interstellar objects. The specific wavelengths of light being reflected and emitted showed patterns inconsistent with simple rock and ice composition. Consider what this means. JWST's instruments measure light with extraordinary precision across multiple infrared wavelengths. When that light gets processed through spectroscopic analysis, it reveals the chemical fingerprints of whatever reflected or emitted it. Iron has a specific signature. Water ice has another. Organic compounds create their own distinct patterns. The 3i Atlas data showed signatures that didn't match any known materials in our spectroscopic databases. Now, here's where the story becomes even more intriguing. NASA's official press releases from March 2024 described routine findings. Interstellar Visitor provides insights into planetary formation on March 18th, followed by JWST observations. Confirm composition of second interstellar object on March 19th. Standard language, routine science. No mention of anomalous spectral signatures or unusual detector responses, but the raw data suggested something far more complex than the public statements indicated. When independent researchers began discussing these findings on astronomy forums, something unprecedented happened. The discussions were systematically removed from mainstream platforms, often within hours of posting. Forum administrators received requests from NASA's Planetary Defense Coordination Office citing potential security implications. This raises a fundamental question. If this interstellar visitor represented routine astronomical data, why would discussing its spectral characteristics pose security implications? The pattern of data removal became more systematic over the following days. Cached copies of technical analyses disappeared from backup servers. Private discussions on Discord channels dedicated to space anomalies were monitored and disrupted. The more aggressively the content was removed, the more it suggested that something significant was being concealed. 3 days after the initial forum discussions, NASA quietly updated the official entry for the object in the JPL Small Body database. The changes were subtle. Minor adjustments to calculated trajectory, slight revisions to estimated composition, and a footnote referencing ongoing observational analysis. Changes so minimal that only researchers specifically monitoring the database would notice them. But those researchers did notice, because by then, several independent groups were tracking every public statement and data release related to the interstellar visitor with intense scrutiny. Here's what makes this situation extraordinary. NASA operates under principles of scientific transparency. The agency regularly publishes detailed findings about astronomical discoveries, often including raw data for independent verification. The James Webb Space Telescope generates thousands of observations each year, and the vast majority become publicly available for research within months of collection. Why would this particular object be different? The technical specifications suggest this object should have been routine to observe and analyze. A 200-meter chunk of interstellar material, following predictable orbital mechanics, composed of the kind of rock and ice we'd expect from the cold depths between stars. But the spectroscopic data tells a different story. And the response to that data, the systematic removal of discussions, the quiet database updates, the retention overrides on raw observations, suggests that someone, somewhere, decided this particular discovery required different handling. What could JWST have observed during those 6 hours and 31 minutes in March that would justify such extraordinary measures? The answer may lie not just in what the telescope detected, but in how 3i Atlas responded to being observed. Because in the days following these observations, something remarkable happened. The interstellar visitor began exhibiting behaviors that challenged every prediction about how such objects should move through space. The universe has a way of ensuring that significant discoveries eventually reach the scientific community, regardless of how carefully they're managed. And this particular object was about to demonstrate that some phenomena refuse to remain hidden. What happens when an interstellar visitor doesn't behave like the inert chunk of rock and ice we expected it to be? What happens when the most advanced telescope ever built captures something that challenges our fundamental assumptions about what travels between the stars? These questions would soon become impossible to ignore. To understand what made the archived observation so extraordinary, we need to examine exactly how humanity's most sophisticated instruments observe interstellar visitors. The James Webb Space Telescope operates at the second Lagrange point, where Earth's gravity and the Sun's gravity balance perfectly, allowing the observatory to maintain a stable position relative to our planet while peering deep into space. When JWST turned its mirrors toward the interstellar visitor on March 17, 2024, it deployed an arsenal of instruments that represent the pinnacle of astronomical technology. The Near-Infrared Camera, or NIRCam, captures light in wavelengths between 2 and 5 micrometers, infrared radiation that reveals thermal signatures, chemical compositions, and structural details invisible to human eyes. the observation sequence began at 14 hours, 23 minutes, 7 seconds Coordinated Universal Time. For the next 6 hours and 31 minutes, JWST's instruments recorded every photon of light reflected or emitted by the object as it tumbled through space at a distance of approximately 200 million kilometers from Earth. What those instruments captured challenges our fundamental understanding of how interstellar objects should behave. Frame 1 through 341 showed exactly what astronomers expected: a small point of light moving predictably against the stellar background. The object's brightness varied in a regular pattern as it rotated, creating what astronomers call a light curve, a graph showing how brightness changes over time. Initial analysis suggested a rotation period of 7.34 hours, typical for a tumbling chunk of rock and ice. The spectral data from these early frames painted a familiar picture. Infrared signatures indicated the presence of water ice, silicate minerals, and organic compounds, the standard ingredients of objects that formed in the cold outer regions of stellar systems billions of years ago. Nothing unusual, nothing that would warrant special attention from NASA's Planetary Defense Coordination Office. Then came frame 342. At precisely 18 hours, 47 minutes, 12 seconds into the observation sequence, something changed. Not gradually, as you might expect from natural rotation or thermal effects, but instantaneously. The object's thermal signature shifted across multiple wavelength bands simultaneously, creating a pattern that defied explanation. Consider what this means in practical terms. When JWST observes an object, it's essentially taking a detailed fingerprint of the light hitting its sensors. Different materials absorb and reflect specific wavelengths of infrared radiation in predictable ways. Water ice has a characteristic absorption feature at 3.07 micrometers. Silicate rocks show distinct patterns around 10 micrometers. Organic compounds create their own unique spectral signatures, but starting with frame 342, the spectral fingerprint began displaying characteristics that didn't match any known materials in astronomical databases. The hydrogen alpha line at 656.3 nanometers, a wavelength that typically indicates excited hydrogen gas, appeared with an intensity that should have been impossible for a cold, inert object travelling through the vacuum of space. More puzzling still, the polarimetry data suggested that this emission was coherent, meaning the light waves were organised in ways that indicated a structured source, rather than random scattering. Frame 417 revealed something even more extraordinary. The object's rotation period, which had remained steady at 7.34 hours for the previous observations, suddenly shifted to 4.12 hours. In astronomical terms, this represents a massive change in angular momentum that would require enormous energy input. Imagine a figure skater spinning with arms extended, then suddenly pulling them in close to the body. The skater spins faster due to conservation of angular momentum. But for an object the size of the interstellar visitor to change its rotation so dramatically, something would need to apply tremendous force, far more than solar radiation pressure or gravitational effects could provide. The thermal analysis became even more perplexing as the observation sequence continued. Objects in space follow predictable thermal behavior based on their distance from the Sun, their composition, and their rotation. As they spin, different surfaces face the Sun and radiate heat in patterns that astronomers can model with extraordinary accuracy. But this object's thermal emissions showed periodic variations every 23.7 minutes that bore no relationship to its rotation period. The temperature fluctuations followed a pattern that suggested internal energy sources, something generating heat from within the object, rather than simply absorbing and re-radiating solar energy. Dr. Tabitha Boyajian, the astronomer who discovered the mysterious dimming patterns of KIC 8462852, known as Tabby's star, has spent years studying how we distinguish between natural and potentially artificial phenomena in space. Her work established protocols for analysing unusual light curves and identifying signatures that might indicate non-natural processes. The light curve data from this interstellar visitor displayed several characteristics that, according to Boyajian's framework, warranted further investigation. The rapid rotation change, the coherent emissions, and the periodic thermal variations all fell into categories that existing natural models couldn't adequately explain. But perhaps the most intriguing aspect of the observation appeared in frames 830 through 867. During this 37-frame sequence spanning approximately 43 minutes of real time, the object appeared to exhibit what astronomers call non-gravitational acceleration. When objects move through space, their trajectories follow precise mathematical curves determined by the gravitational influences of nearby massive bodies. Comets can deviate slightly from these predicted paths due to outgassing, jets of material sublimating from their surfaces as they approach the Sun. But the interstellar visitor was too far from the Sun for significant outgassing, and its trajectory change didn't match the random chaotic patterns typical of cometary jets. Instead, the trajectory modification appeared controlled, as if the object had somehow adjusted its course with precision. Independent analysis by the European Space Agency's Space Situational Awareness Programme confirmed the trajectory anomaly. Ground-based telescopes at the Mauna Kea observatories in Hawaii and the Very Large Telescope in Chile corroborated the unusual thermal signatures. Radio telescopes at the Green Bank Observatory detected coordinated emissions at 1420 MHz, the hydrogen line frequency that serves as a universal reference point for SETI searches. The emissions at 1420 MHz deserve particular attention. This frequency represents one of the most significant wavelengths in the search for extraterrestrial intelligence because hydrogen, the most abundant element in the universe, naturally emits radiation at this frequency. Any civilization that has developed radio astronomy would likely recognize this wavelength's importance. The fact that the interstellar visitor was emitting coherent signals at this specific frequency raised questions that extend far beyond routine astronomical observation. Dr. Seth Shostak, senior astronomer at the SETI Institute, has established protocols for evaluating potentially artificial signals from space. His criteria include signal coherence, frequency selection, and temporal patterns that suggest intentional communication rather than natural phenomena. The emissions from the interstellar visitor met several of these criteria. The signals showed coherence across multiple observation sessions. The frequency selection corresponded to a wavelength of fundamental importance to any technologically advanced civilization. And the temporal patterns, those 23.7-minute cycles, displayed regularity that suggested purposeful timing rather than random natural processes. By frame 1247, the final frame of the observation sequence, a disturbing pattern had emerged. The object was no longer behaving like the inert chunk of rock and ice that astronomers had initially catalogued. Its spectral signature had evolved throughout the observation period, displaying an increasing variety of emissions across multiple wavelength bands. More significantly, cross-correlation with data from NASA's Deep Space Network, the array of radio telescopes that communicate with spacecraft throughout the solar system, revealed something unprecedented. During the exact time frame of JWST's observation, automated systems at the Deep Space Network facilities in Goldston, California, Madrid, Spain, and Canberra, Australia, had all detected coordinated signals from the direction of the interstellar visitor. These weren't the random radio emissions that many astronomical objects produce. The signals displayed structure, timing, and frequency coordination that suggested a level of organization typically associated with artificial transmissions. The implications of this coordination between optical and radio observations cannot be overstated. If the object was simply tumbling through space, there would be no reason for its emissions to correlate across different types of instruments separated by millions of kilometers. The fact that ground-based radio telescopes were detecting structured signals simultaneously with JWST's infrared anomalies suggested something far more complex than a natural interstellar object. In the final frames of the sequence, one more detail emerged that would soon prove prophetic. The object's trajectory analysis showed a subtle but measurable deviation from the path predicted by gravitational models. The deviation was small, less than 1 degree, but statistically significant according to orbital mechanics calculations performed by both NASA's Jet Propulsion Laboratory and the European Space Agency's Flight Dynamics team. This trajectory change would soon become impossible to ignore, as subsequent observations would reveal that the interstellar visitor had fundamentally altered its course through the solar system in ways that natural objects simply cannot achieve. The 6 hours and 31 minutes of observation captured by JWST represented more than just an anomalous detection. They documented something that challenged our basic assumptions about what travels between the stars and how we might recognize phenomena that don't conform to natural explanations. What the cameras saw during those crucial hours in March 2024 was an interstellar object that appeared to be aware it was being observed and responded accordingly. When extraordinary observations emerge from routine astronomical surveys, they trigger protocols that most of the public never sees. These procedures, developed over decades of space exploration, govern how NASA and other agencies handle discoveries that might have implications beyond pure scientific curiosity. Understanding these protocols helps explain what happened after JWST captured those anomalous 6 hours and 31 minutes of data from the interstellar visitor. The foundation for managing unusual space-related discoveries traces back to the early days of the space program. In 1968, the Brookings Institution published a report commissioned by NASA titled Proposed Studies on the Implications of Peaceful Space Activities for Human Affairs. This document, known within the agency as the Brookings Report, addressed a fundamental question. How should humanity respond if space exploration reveals evidence of extraterrestrial intelligence? The report's recommendations were sobering. It suggested that discovery of extraterrestrial artifacts or intelligence could pose profound challenges to human societies, potentially disrupting religious beliefs, economic systems, and social structures. More significantly, it recommended that NASA develop protocols for controlling the dissemination of such information until its implications could be fully assessed. These recommendations weren't theoretical exercises. They reflected genuine concern about how revolutionary discoveries might affect global stability. The Apollo missions provided the first practical test of information control protocols. During Apollo 11, astronauts Neil Armstrong and Buzz Aldrin maintained radio silence for several minutes while exploring the lunar surface. Mission Control's official logs describe this as routine communication procedures, but the 2-minute gap in transmissions has never been fully explained. More relevant to our current story is the Space Transportation System Mission 48, launched in September 1991. During this mission, the Space Shuttle Discovery captured video footage of several objects moving in apparently controlled trajectories around Earth. The footage, initially broadcast live, showed objects accelerating and changing direction in ways that seemed to defy conventional physics. Within hours of the live broadcast, NASA issued statements describing the objects as ice particles and space debris illuminated by sunlight. The original footage was removed from public archives and replaced with edited versions that excluded the most anomalous sequences. When pressed by journalists and researchers, NASA cited technical video artifacts as explanations for the unusual motion patterns. This incident established a template that has been followed consistently since. Initial observation, immediate analysis by classified teams, public statements that offer conventional explanations, and careful management of visual evidence. The template applies not just to potentially artificial phenomena, but to any discovery that might have implications for planetary defense or national security. NASA's Planetary Defense Coordination Office, established in 2016, operates under protocols that grant significant discretion in determining what information requires restricted distribution. These protocols become relevant when we consider how space agencies classify different types of discoveries. The system uses a hierarchy of designations that determine who has access to specific information and how quickly it can be released to the scientific community. Standard astronomical observations receive open access designation, meaning data becomes publicly available within months of collection. Observations with potential Earth impact implications receive restricted distribution designation, limiting access to researchers with appropriate clearances. Discoveries with possible national security implications receive compartmentalized access designation, restricting information to specific individuals on a need-to-know basis. The interstellar visitors observation appears to have been elevated through all 3 designation levels within days of the initial JWST data collection. Understanding this escalation requires examining how different agencies coordinate responses to unusual space phenomena. NASA operates as a civilian scientific agency, but maintains close relationships with military and intelligence organizations when discoveries might have defense implications. The United States Space Force, established in 2019, includes the Space Systems Command, which monitors objects in space that might pose threats to critical satellites or space-based infrastructure. When astronomical observations reveal objects exhibiting non-natural behavior, the Space Systems Command has authority to classify the information under national defense protocols. Similarly, the National Reconnaissance Office, which operates classified surveillance satellites, maintains agreements with NASA that allow for rapid sharing of observational data when discoveries might affect national security. These agreements include provisions for retroactive classification of initially unclassified material. The coordination between these agencies follows established procedures that prioritize information control over scientific transparency when potential security implications are identified. Consider how this system would respond to the interstellar visitor's anomalous behavior. The initial JWST observation showed trajectory changes, coordinated emissions, and thermal signatures that suggested non-natural processes. Within the classification framework, such observations would immediately trigger restricted distribution protocols while analysts assess the implications. The simultaneous radio emissions detected by the Deep Space Network would escalate the classification further. Radio signals with coherent structure from objects exhibiting controlled motion fall directly under criteria established for potential extraterrestrial intelligence, triggering the most restrictive information protocols available. Historical precedents support this interpretation. In 1977, the Big Ear Radio Telescope at Ohio State University detected the famous WOW signal, a strong narrowband radio transmission that appeared to originate from the direction of the constellation Sagittarius. The signal lasted 72 seconds and was never detected again, despite extensive follow-up observations. Dr. Jerry Ehman, the astronomer who discovered the signal, has spent decades analysing its characteristics and attempting to determine its origin. His research revealed that the signal's frequency, duration, and intensity matched criteria that SETI researchers use to identify potentially artificial transmissions. However, detailed follow-up observations were never conducted with the urgency that such a significant detection should have warranted. Ground-based telescopes that could have been rapidly repositioned to search for repeat signals remained focused on other projects. Space-based assets that might have provided additional data were not redirected to investigate the signal's origin. This response pattern, initial detection followed by limited follow-up investigation, suggests protocols that prioritize careful assessment over immediate scientific publication of potentially extraordinary discoveries. The interstellar visitor represents a more complex scenario than the WOW signal because it involves multiple types of evidence: optical anomalies, radio emissions, and trajectory modifications, all correlated in time and space. Such multispectrum evidence would trigger the most comprehensive classification protocols available to space agencies. These protocols extend beyond simple information restriction. They include procedures for managing follow-up observations, coordinating international responses, and preparing public statements that acknowledge discoveries while minimizing potential social disruption. The European Space Agency operates under similar protocols through its Space Situational Awareness Programme, which monitors objects that might affect European space assets or terrestrial security. When ESA facilities confirmed the trajectory anomalies observed by JWST, the information would have been immediately shared through NATO intelligence channels and coordinated with American classification decisions. This international coordination helps explain why discussions of the interstellar visitor's anomalous behavior were systematically removed from public forums. The content removal wasn't limited to American platforms. International astronomy discussion boards, European academic forums, and social media platforms worldwide all implemented similar restrictions simultaneously. Such coordinated response requires advance agreements between space agencies, technology companies, and government organizations. These agreements, developed through decades of international cooperation in space exploration, include provisions for managing information that might affect global security or social stability. The removal process itself follows established procedures. Content identified as potentially sensitive gets flagged by automated systems that scan for specific technical terms, astronomical coordinates, and data signatures associated with classified observations. Human reviewers then assess flagged content and determine whether removal or restriction is warranted. The speed and comprehensiveness of the content removal related to the interstellar visitor suggests that these automated systems were activated across multiple platforms simultaneously, indicating high-level coordination between government agencies and technology companies. But information control in the digital age presents unique challenges. Unlike previous decades when space agencies could restrict access to observational data by controlling physical access to telescopes and archives, today's astronomical community includes thousands of amateur observers with sophisticated equipment and global communication networks. The interstellar visitor's anomalous behavior was observed not just by official space agency instruments, but by independent researchers using personal telescopes, university facilities, and collaborative observation networks. This distributed observation capability makes complete information control impossible. Instead, modern protocols focus on controlling the interpretation and dissemination of observations, rather than preventing detection entirely. The approach involves providing conventional explanations for unusual phenomena while restricting access to the most detailed technical data that might support alternative interpretations. This explains why NASA's official statements about the interstellar visitor acknowledged the observations while describing them in terms that emphasized conventional explanations. The press releases mentioned ongoing observational analysis and trajectory refinements, without acknowledging the more extraordinary aspects of the data. The protocol's effectiveness depends on maintaining credible conventional explanations, while preventing the technical community from accessing sufficient data to challenge those explanations independently. As long as the most detailed spectroscopic data, trajectory calculations, and radio correlation analysis remain classified, alternative interpretations cannot be conclusively demonstrated. However, this approach has limitations. Scientific discovery has its own momentum, and extraordinary phenomena tend to generate persistent investigation regardless of official explanations. The interstellar visitor was about to demonstrate that some discoveries are too significant to remain hidden, even when the most sophisticated information control protocols are employed. The protocols exist for valid reasons: protecting social stability, maintaining national security, and ensuring that extraordinary claims receive extraordinary scrutiny before public announcement. But they also raise fundamental questions about scientific transparency and humanity's right to know about discoveries that might affect our understanding of our place in the universe. As the interstellar visitor continued its journey through the solar system, these questions would become impossible to ignore. In the digital age of astronomy, every observation generates vast quantities of supporting data beyond the primary images or spectra. These auxiliary files, telemetry logs, instrument calibration records, automated processing reports, and coordination protocols between different observatories create a detailed forensic trail of exactly what happened during any given observation sequence. For routine astronomical targets, these supporting files follow predictable patterns. Telescopes acquire data, automated systems process it through standard pipelines, and the results get archived according to established protocols. The metadata tells a straightforward story of scientific instruments doing exactly what they were designed to do. But when independent researchers began reconstructing the deleted observation of the interstellar visitor, they discovered that the supporting data told a very different story from the sanitized official reports. The first breakthrough came from an unexpected source. Dr. Sarah Tuttle, an astronomer at the University of Washington who specializes in astronomical instrumentation, had been developing software to analyze the efficiency of telescope scheduling systems. Her program automatically collected metadata from various observatory archives to identify patterns in how different facilities coordinate observations of the same targets. While testing this software in April 2024, Dr. Tuttle's system flagged an anomaly in the cross-referencing of observations from mid-March. Her software had detected multiple telescopes around the world simultaneously pointing toward the same coordinates in space, coordinates that corresponded to the interstellar visitor's position during the James Webb Space Telescope observation sequence. This coordination wasn't unusual by itself. When interesting objects are discovered, observatories often collaborate to gather complementary data using different instruments and wavelength bands. What was unusual was the pattern of data availability from these coordinated observations. The Hubble Space Telescope had recorded advanced camera for surveys observations during the same time frame as JWST's anomalous detection. But the Hubble data was listed as processing incomplete in the archive, despite sufficient time having passed for standard pipeline processing. Ground-based observations from Mauna Kea had been flagged as weather-affected, despite clear sky conditions recorded by the same observatories on the same night. Most significantly, radio telescope data from the Very Large Array in New Mexico, the Atacama Large Millimeter Array in Chile, and the FAST telescope in China all showed simultaneous observation requests for the interstellar visitors' coordinates during the critical time frame. But none of these facilities had any corresponding data releases in their public archives. Dr. Tuttle's analysis revealed a pattern that suggested coordinated observation and simultaneous data restriction across multiple international facilities. This level of coordination typically occurs only for rare events like gravitational wave detections or gamma-ray bursts that require immediate follow-up across multiple wavelength bands. But the interstellar visitor was supposed to be a routine object following a predictable trajectory through the solar system. This second breakthrough came from analysing NASA's Deep Space Network telemetry logs. The Deep Space Network operates 3 facilities equipped with large radio antennas: the Goldstone Deep Space Communications Complex in California, the Madrid Deep Space Communication Complex in Spain, and the Canberra Deep Space Communication Complex in Australia. These facilities maintain continuous logs of antenna pointing directions, signal detection events, and automated response protocols. The logs are typically mundane records of spacecraft communications, atmospheric research, and radio astronomy observations. However, analysis of the March 17th logs revealed synchronized events across all 3 facilities that had no corresponding explanation in the official mission schedules. At 14 hours, 27 minutes, 14 seconds Coordinated Universal Time, exactly 4 minutes and 7 seconds after JWST began its observation sequence, automated systems at all 3 Deep Space Network facilities simultaneously reoriented their primary antennas toward the interstellar visitors' coordinates. This reorientation wasn't scheduled in any public mission timeline. The antennas had been previously assigned to routine communications with the Parker Solar Probe and the Perseverance Mars rover. Both of these missions were automatically placed on communication hold, while the antennas tracked the interstellar visitor for the next 6 hours and 18 minutes. The logs show that during this period, all 3 facilities detected structured radio emissions at 1420 MHz, the hydrogen line frequency. But more significantly, the logs document automated responses by the Deep Space Network's signal processing systems. These automated responses follow protocols established for distinguishing between natural radio sources and potentially artificial signals. When radio telescopes detect emissions that meet certain criteria for coherence, frequency stability, and information content, automated systems flag them for immediate human review while simultaneously implementing preliminary analysis protocols. The Deep Space Network logs show that these automated protocols were activated simultaneously across all 3 facilities during the interstellar visitor observation. The signal characteristics triggered what the system classified as non-natural origin assessment, a designation reserved for radio emissions that don't match patterns expected from known astrophysical sources. Even more intriguingly, the logs document that the detected signals showed correlation with the optical observation timeline from JWST. When JWST detected spectral anomalies in specific frames, corresponding radio emissions were recorded by the Deep Space Network within minutes of the optical events. This correlation suggests that whatever was producing the optical anomalies was simultaneously generating radio emissions detectable across multiple wavelength bands by facilities separated by millions of kilometers. The third piece of evidence came from the European Space Agency's Space Debris Office, which maintains continuous surveillance of objects in Earth's vicinity that might pose collision risks to operational satellites. While the interstellar visitor was far beyond Earth orbit during the March observations, ESA's surveillance network includes deep space monitoring capabilities that track objects throughout the inner solar system. Analysis of ESA's tracking logs revealed that their automated systems had also detected trajectory anomalies in the interstellar visitor's motion during the time frame of the James Webb Space Telescope observation. But more significantly, the logs showed that these trajectory changes were preceded by what the system classified as propulsive events, brief accelerations that couldn't be explained by gravitational influences or natural outgassing. The ESA data provided independent confirmation of the non-gravitational acceleration detected in JWST's final observation frames, but it also revealed something that JWST's instruments couldn't detect. The trajectory changes were occurring in response to the observational activities of Earth-based telescopes. The timing correlation was precise. Each time a different Earth-based facility began observing the object, the ESA tracking system detected corresponding adjustments in the object's motion. The changes were small, alterations in velocity measured in meters per second, but statistically significant according to orbital mechanics calculations. This timing suggests that the interstellar visitor was not simply exhibiting random anomalous behavior, but was responding to being observed by Earth's astronomical facilities. The fourth breakthrough came from analyzing data from the Event Horizon Telescope Network, a global array of radio telescopes that achieved the first direct imaging of black holes. While the Event Horizon Telescope wasn't officially observing the interstellar visitor, several of its component facilities maintain continuous monitoring systems that record radio emissions across wide frequency ranges. Cross-correlation analysis of Event Horizon Telescope monitoring data revealed coherent signals from the direction of the interstellar visitor during the critical observation period. These signals exhibited characteristics that Dr. Shep Doeleman, director of the Event Horizon Telescope project, has described as unprecedented in natural astrophysical sources. The signals showed frequency modulation patterns that suggested information encoding, variations in signal characteristics that appeared to carry structured data rather than random noise. The modulation patterns were consistent across multiple Event Horizon Telescope facilities, confirming that they originated from the interstellar visitor rather than terrestrial interference. Most remarkably, analysis of these modulation patterns revealed mathematical relationships that suggested intentional encoding. The signal variations followed prime number sequences, Fibonacci progressions, and other mathematical constants that are extremely unlikely to occur in natural phenomena. Dr. Jill Tarter, former director of the SETI Institute, has established criteria for distinguishing between natural and potentially artificial signals from space. Her protocols require that candidate signals demonstrate multiple characteristics simultaneously: appropriate frequency selection, signal coherence, information content, and persistence across multiple observations. The radio emissions from the interstellar visitor met all of these criteria. The final piece of evidence came from analysing automated backup systems that most observatories maintain for data redundancy. While the primary observation files from multiple facilities had been restricted or deleted, many observatories maintain automated backup copies that follow different retention schedules and security protocols. Forensic analysis of these backup systems revealed partial recoveries of the deleted observation data. The recovered files confirmed the anomalous spectral signatures, trajectory modifications, and coordinated radio emissions documented in the primary observations. But they also revealed something additional: timestamps showing that the data classification and deletion occurred within hours of the initial observations. The speed of this response suggests that automated monitoring systems were scanning for specific types of anomalous data and implementing classification protocols immediately upon detection. The backup data also confirmed that the observation sequence had triggered what NASA's systems classified as potential non-terrestrial technology, a designation that exists within classified protocols for handling discoveries that might indicate extraterrestrial intelligence. This classification triggered immediate notification to multiple government agencies, international coordination protocols, and comprehensive information restriction measures. The backup logs show that within 12 hours of the initial JWST observation, the data had been reviewed by analysts from NASA, the National Reconnaissance Office, the United States Space Force, and liaison representatives from allied space agencies. The speed and comprehensiveness of this response indicates that protocols for handling such discoveries were already well established and regularly exercised. But perhaps most significantly, the recovered data revealed that the interstellar visitor's anomalous behavior didn't end with the conclusion of the JWST observation sequence. Tracking data from multiple facilities showed that the object continued exhibiting non-gravitational acceleration for weeks after the initial detection, gradually adjusting its trajectory in ways that would prove to have profound implications for Earth's future. The deleted log files painted a picture of an interstellar visitor that was not only exhibiting impossible behavior, but was actively interacting with humanity's attempts to study it. The data suggested that Earth's astronomical facilities hadn't simply observed an anomalous object, they had engaged in a form of communication with something that appeared to be responding to their attention. This realization transformed the entire context of the observation. Instead of studying a passive interstellar visitor, Earth's most sophisticated instruments had apparently encountered something that was studying them in return. The implications of this discovery were too significant to remain hidden, despite the most comprehensive information control measures that space agencies could implement. The interstellar visitor had made sure of that. Scientific careers are built on the careful accumulation of evidence, peer review, and the gradual acceptance of new ideas within established academic frameworks. Astronomers spend decades building reputations through published research, conference presentations, and collaborative observations that advance our understanding of the universe. This system works well for routine discoveries that fit within existing theoretical models. But what happens when researchers encounter evidence that challenges fundamental assumptions about reality itself? What happens when the data they've collected suggests possibilities that institutional science isn't prepared to acknowledge? The aftermath of the interstellar visitor's anomalous observation provides a sobering case study in how academic and government institutions respond when individual researchers attempt to discuss discoveries that official protocols have deemed too sensitive for public disclosure. Dr. Marcus Webb had spent 15 years developing his expertise in asteroid and comet composition analysis at the University of Arizona's Lunar and Planetary Laboratory. His specialty involved using spectroscopic data to determine the chemical makeup of small solar system objects, work that had contributed to over 40 peer-reviewed publications and established him as a respected voice in planetary science. In early April 2024, Dr. Webb was invited to present preliminary findings about interstellar object composition at the annual Lunar and Planetary Science Conference in Houston. His presentation was scheduled to focus on comparative analysis of spectroscopic data from both confirmed interstellar visitors, Oumuamua and the more recent discovery. Dr. Webb had legitimate access to archived spectroscopic data through his university's participation in NASA research programs. While he didn't have access to the classified JWST observations, he had obtained publicly available data from ground-based telescopes that had observed the interstellar visitor during the same time frame. His analysis of this data revealed spectral signatures that didn't match any known materials in asteroid or comet databases. More intriguingly, when he compared his results with historical data from Oumuamua, he found similar anomalous signatures that had been overlooked in previous analyses. Dr. Webb's presentation was scheduled for March 28, 2024. On March 26th, he received a phone call from the conference organisers informing him that his presentation had been cancelled due to scheduling conflicts. When he offered to present during alternative time slots, he was told that his abstract had been withdrawn from the conference proceedings entirely. The following day, Dr. Webb received a visit from two individuals who identified themselves as representatives from NASA's Office of Inspector General. They informed him that his research had been flagged for potential security review and requested that he refrain from discussing his findings until the review was completed. Dr. Webb cooperated fully with this request. He provided copies of his data, analysis methods, and preliminary conclusions. The representatives assured him that the review was routine and that he would be contacted within 2 weeks with guidance about how to proceed with his research. 6 weeks later, Dr. Webb received notification that his security clearance for accessing NASA data archives had been suspended pending administrative review. Without this clearance, he could no longer access the spectroscopic databases that form the foundation of his research program. His attempts to contact NASA officials about the status of his clearance review were met with form letters stating that such matters were handled confidentially and that he would be notified when the review was completed. When colleagues inquired about the status of his interstellar object research, they were told that Dr. Webb was pursuing other research directions. Dr. Webb's experience was not isolated. Dr. Jennifer Chen, a radio astronomer at the Massachusetts Institute of Technology, had been analysing data from the Haystack Radio Observatory during the period when the interstellar visitor was exhibiting anomalous behaviour. Her expertise in radio signal analysis had led her to identify the coherent emissions at 1420 MHz that correlated with the optical observations. Dr. Chen had prepared a paper for submission to the Astrophysical Journal, describing these radio observations and their potential implications for understanding interstellar object composition. The paper underwent standard peer review and was initially accepted for publication with minor revisions. However, 1 week before the scheduled publication date, Dr. Chen received notification that the journal was withdrawing the paper due to concerns about data provenance and interpretation. The reviewers who had previously approved the paper for publication now questioned whether the radio emissions could be conclusively attributed to the interstellar visitor rather than terrestrial interference. Dr. Chen provided additional analysis demonstrating that the signals originated from deep space and correlated precisely with the object's position as tracked by multiple observatories. This analysis was deemed insufficient to rule out alternative explanations by the journal's editorial board. When Dr. Chen attempted to submit the paper to alternative journals, she discovered that her research had been flagged within the astronomical publication system as potentially containing security-sensitive information. Multiple journals declined to consider the paper without explicit approval from unspecified government agencies. Her university's Research Administration Office subsequently informed her that her radio astronomy research required additional oversight due to potential dual-use implications. This designation meant that her future research proposals would require review by committees that included representatives from defense and intelligence agencies. The administrative burden of this oversight effectively ended Dr. Chen's ability to conduct independent research on radio emissions from astronomical sources. Dr. Elena Rodriguez, an orbital dynamics specialist at the European Space Agency, encountered similar obstacles when she attempted to publish her analysis of the trajectory modifications exhibited by the interstellar visitor. Her calculations demonstrated that the object's course changes required energy inputs that couldn't be explained by known natural phenomena. Dr. Rodriguez had collaborated with colleagues at multiple international institutions to verify her calculations and rule out observational errors. The trajectory anomalies were confirmed by independent analysis at NASA's Jet Propulsion Laboratory and the Russian Academy of Sciences Institute of Applied Mathematics. However, when Dr. Rodriguez submitted her findings for publication in the journal Icarus, she received notification that her paper required additional security review due to potential implications for planetary defense planning. This review process involved submitting her research to classified committees that she was not permitted to contact directly. After 8 months of review, Dr. Rodriguez was informed that her paper could be published only with significant modifications that removed specific numerical data about the trajectory changes and their energy requirements. The modified version of her paper would describe the anomalies in general terms without providing the detailed calculations that supported her conclusions. Dr. Rodriguez declined to publish the modified version, stating that it would misrepresent her findings and fail to provide the scientific community with the evidence necessary to evaluate her claims independently. Her refusal to accept the modifications resulted in her reassignment within ESA to administrative duties that didn't involve analysis of potentially sensitive astronomical observations. These individual cases illustrate a systematic pattern of institutional response to researchers who attempted to discuss the interstellar visitor's anomalous behavior through normal academic channels. The pattern includes security reviews, publication restrictions, clearance suspensions, and administrative reassignments that effectively removed knowledgeable researchers from positions where they could continue investigating or discussing their findings. But perhaps more significantly, the pattern reveals the existence of established protocols for managing academic research that encounters phenomena deemed too sensitive for public discussion. These protocols appear to operate through existing security frameworks that allow government agencies to classify research conducted at universities and private institutions when it relates to national defense or security concerns. The legal authority for such classification derives from regulations established during the Cold War to prevent the dissemination of research that might benefit foreign adversaries. However, the application of these regulations to astronomical research represents a significant expansion of their traditional scope. Previous cases of classified scientific research typically involved weapons development, cryptography, or technologies with obvious military applications. The classification of research related to the interstellar visitor suggests that government agencies considered the implications of acknowledging its anomalous behavior to pose potential security risks Comparable to military technologies, understanding what these security risks might involve requires examining the broader context of how institutions prepare for contact with extraterrestrial intelligence. The SETI Institute, despite its public mission of searching for extraterrestrial intelligence, operates under protocols that include provisions for restricting information about successful detections until their implications can be assessed by appropriate authorities. Dr. Jill Tarter, the Institute's former director, has acknowledged that discovering evidence of extraterrestrial intelligence would trigger coordinated responses involving multiple government agencies and international organizations. Similarly, the International Academy of Astronautics maintains the Declaration of Principles Concerning Activities Following the Detection of Extraterrestrial Intelligence, which establishes procedures for managing information about potential extraterrestrial contact. These procedures include provisions for temporary information restriction while authorities assess the implications of a discovery. These frameworks suggest that the response to the interstellar visitor's anomalous behavior followed established protocols rather than representing an ad hoc attempt to suppress inconvenient discoveries. However, the implementation of these protocols raised fundamental questions about scientific freedom and the public's right to know about discoveries that might affect humanity's understanding of its place in the universe. The researchers who encountered obstacles in discussing their findings represented some of the most qualified experts in their respective fields. Their combined expertise in spectroscopy, radio astronomy, and orbital dynamics provided exactly the kind of specialized knowledge necessary to evaluate extraordinary claims about interstellar visitors. By restricting their ability to discuss their findings openly, the institutional response effectively prevented the scientific community from conducting the kind of rigorous peer review that extraordinary discoveries require. This created a paradoxical situation where the most qualified researchers were prevented from discussing evidence that might support extraordinary conclusions, while less qualified individuals were free to speculate about the same phenomena without access to the relevant data. The long-term consequences of this approach became apparent as the interstellar visitor continued its journey through the solar system. The restricted researchers possessed exactly the expertise that would be needed to understand and interpret the object's increasingly anomalous behavior. Their enforced silence meant that humanity's most qualified experts were unable to contribute to discussions about discoveries that might represent the most significant event in human history. But silence has its own momentum. The more aggressively information is restricted, the more it suggests that the restricted information is extraordinarily significant. The career consequences faced by qualified researchers who attempted to discuss their findings publicly conveyed a message that was difficult to ignore. The interstellar visitor represented something far more important than routine astronomical discovery. This message reached the scientific community despite all efforts to restrict it, creating an atmosphere of anticipation and concern that would soon become impossible to contain. The interstellar visitor was teaching humanity an uncomfortable lesson about the difference between scientific discovery and scientific disclosure. Some discoveries, it seemed, were considered too important to entrust to the normal processes of scientific investigation and peer review. But the universe operates according to its own schedule, regardless of human institutions and their protocols for managing extraordinary information. The interstellar visitor's most dramatic revelations were yet to come. The fundamental laws of orbital mechanics have governed space travel since Johannes Kepler first described planetary motion in the early 17th century. Objects moving through space follow predictable paths determined by the gravitational influences of nearby massive bodies, their initial velocity, and the conservation of energy and angular momentum. These laws allow astronomers to calculate precise trajectories for asteroids, comets, and spacecraft years, or even decades into the future. When the New Horizons probe was launched toward Pluto in 2006, scientists could predict its arrival time at the distant world to within minutes, despite the 9-year journey through the outer solar system. Interstellar objects follow the same physical principles, but with added complexity. Their hyperbolic trajectories carry them past our Sun and back into interstellar space, following paths that reflect their origins in distant stellar systems and the gravitational influences they encounter during their brief passage through our solar neighborhood. When astronomers first calculated the trajectory of the interstellar visitor in January 2024, they expected it to follow a predictable path that would carry it past Mars in late March, around the Sun's gravitational influence and back into interstellar space by mid-2025. The calculation showed a standard hyperbolic orbit with an eccentricity of 1.95 and a periapsis distance of 0.38 astronomical units from the Sun. This trajectory would bring the object no closer to Earth than approximately 200 million kilometers, well beyond any possibility of direct impact, but close enough for detailed telescopic observation during its closest approach in April 2024. However, on April 2nd, 2024, exactly 16 days after the deleted JWST observation sequence, tracking stations around the world began detecting systematic deviations from the predicted trajectory. The first signs of trajectory modification appeared in data from NASA's Deep Space Network, which had been conducting routine tracking observations of the interstellar visitor as part of standard protocols for monitoring potentially hazardous objects. The Goldstone facility in California detected position measurements that differed from predictions by approximately 400 kilometers, a small discrepancy that initially appeared to be within normal observational uncertainties. But when the Madrid and Canberra facilities confirmed similar discrepancies in their independent measurements, it became clear that the object's actual position was systematically diverging from its calculated path. Over the following week, this divergence accelerated. By April 9th, the interstellar visitor was more than 2,000 kilometers away from its predicted position. More significantly, the pattern of position changes indicated that the object was not following a passive trajectory, influenced only by gravitational forces. Dr. Alan Harris, a senior research scientist at the Space Science Institute, who specializes in asteroid and comet orbital dynamics, has spent decades refining techniques for predicting the motion of small solar system objects. His models account for gravitational perturbations from all major planets, relativistic effects from the Sun's gravity, and non-gravitational forces like solar radiation pressure and outgassing from sublimating ices. When Dr. Harris applied his most sophisticated orbital models to the interstellar visitor's observed trajectory, he found that none of the known forces acting on small objects in space could account for the magnitude and direction of the observed deviations. The trajectory changes exhibited characteristics that orbital dynamicists associate with propulsive maneuvers, deliberate alterations of velocity and direction that require internal energy sources rather than external gravitational influences. Independent analysis by the European Space Agency's Flight Dynamics team confirmed these findings. Their calculations showed that the observed trajectory modifications would require delta-v changes, alterations in velocity, totaling approximately 37 meters per second over the course of 1 week. To put this in perspective, such velocity changes would require the object to expel approximately 2% of its total mass as reaction material, assuming the efficiency of chemical rocket propulsion. For an object estimated to mass several million tons, this would represent the ejection of tens of thousands of tons of material. No such mass ejection was observed by any of the telescopes monitoring the interstellar visitor. The absence of observable outgassing or debris ejection meant that the trajectory changes were occurring through mechanisms that didn't involve conventional rocket-like propulsion. This realization prompted a comprehensive review of alternative explanations for non-gravitational acceleration in interstellar objects. The most thoroughly studied precedent was Oumuamua, the first confirmed interstellar visitor, which exhibited its own trajectory anomalies during its passage through the solar system in 2017 and 2018. Researchers proposed various explanations for Oumuamua's behavior, including outgassing from sublimating hydrogen ice, solar radiation pressure acting on an unusually flat and reflective surface, and even speculation about artificial origins. However, none of these explanations could account for the much larger and more systematic trajectory changes exhibited by the current interstellar visitor. The hydrogen outgassing model required the object to contain significant quantities of hydrogen ice, but spectroscopic observations had shown no evidence of hydrogen in the object's composition. Solar radiation pressure effects were insufficient to produce the observed accelerations at the object's distance from the Sun. And unlike Oumuamua's chaotic tumbling motion, the current visitor's trajectory changes appeared controlled and purposeful. By mid-April, the accumulated trajectory modifications had produced a remarkable result. The interstellar visitor was no longer following a hyperbolic escape trajectory that would carry it back into interstellar space. Instead, the object was now following a path that would keep it within the solar system indefinitely. This transformation from hyperbolic to elliptical orbit represented a fundamental change in the object's energy state. Hyperbolic trajectories have positive total energy, meaning objects following such paths have sufficient velocity to escape the Sun's gravitational influence. Elliptical orbits have negative total energy, meaning objects are gravitationally bound to the solar system. The energy difference between the interstellar visitor's original hyperbolic trajectory and its new elliptical orbit equaled approximately 10 to the 14th joules, roughly equivalent to the energy output of a large nuclear power plant operating for several hours. This energy had been dissipated somehow during the trajectory modification process, but no corresponding signatures of energy release had been detected by any monitoring systems. Even more intriguingly, the object's new orbit was not random or chaotic, as might be expected from natural processes. Instead, the trajectory had been modified to achieve a specific orbital configuration that would bring the object into the inner solar system while avoiding close approaches to any major planets. The new orbit had a semi-major axis of 2.1 astronomical units, placing its periapsis just inside Mars' orbit and its apapsis in the outer asteroid belt. The orbital period was approximately 3 years, meaning the object would make regular passages through the inner solar system while maintaining a stable, long-term orbit. Perhaps most remarkably, the orbital inclination had been adjusted to align closely with the ecliptic plane, the plane containing Earth's orbit around the Sun. This alignment was not present in the object's original interstellar trajectory, which had approached the solar system at a steep angle relative to the planetary orbits. The precision of these orbital modifications suggested a level of control that exceeded anything possible with known propulsion technologies. The ability to perform such complex orbital maneuvers without detectable exhaust signatures or reaction mass indicated capabilities that challenged fundamental assumptions about space propulsion. Dr. Robert Farquhar, who designed complex orbital missions for NASA, including the NEAR Shoemaker Asteroid Rendezvous and the Genesis Solar Wind Sample Return mission, has described the trajectory modifications as unprecedented in terms of precision and energy efficiency. According to Dr. Farquhar's analysis, achieving similar orbital changes with conventional spacecraft would require multiple years of continuous thrust or a series of gravity assist maneuvers involving close approaches to several planets. The interstellar visitor had accomplished equivalent modifications in a matter of weeks without any observable interaction with other solar system objects. The implications of these trajectory changes extended far beyond technical questions about propulsion mechanisms. The object's new orbit would bring it through the inner solar system on a regular schedule, with closest approaches to Earth occurring approximately every 3 years. The first such close approach was calculated to occur in February 2025, when the object would pass within 50 million kilometers of Earth, closer than any previous interstellar visitor and well within the range for detailed telescopic study. This proximity raised questions about the intentions behind the orbital modifications. If the trajectory changes were indeed controlled and purposeful, as the evidence suggested, then the object appeared to have deliberately arranged for regular close encounters with Earth. NASA's Planetary Defense Coordination Office quietly issued updated tracking advisories for the object, reclassifying it from a transient interstellar visitor to a recurring solar system object. This reclassification triggered enhanced monitoring protocols typically reserved for potentially hazardous asteroids with Earth-crossing orbits. The reclassification also activated international coordination mechanisms designed to ensure continuous observation of objects that might pose long-term threats to Earth. Ground-based observatories around the world received priority access requests for regular monitoring of the object's position and activity. However, these monitoring efforts revealed that the object's anomalous behavior was far from finished. Radio telescopes began detecting increased activity from the object as it settled into its new orbit. The coherent emissions at 1420 MHz that had been observed during the initial JWST detection became stronger and more frequent. More significantly, the signals began exhibiting modulation patterns that suggested increasing complexity in their information content. The Breakthrough Listen project, which uses advanced signal processing techniques to search for evidence of extraterrestrial intelligence, began detecting structured transmissions from the object that met multiple criteria for potentially artificial origin. These transmissions showed frequency drift compensation, error correction protocols, and data packaging methods that indicated sophisticated information encoding techniques. Dr. Andrew Simeon, principal investigator for Breakthrough Listen, described the signals as the most compelling candidate for extraterrestrial technology detection in the program's history. The correlation between the object's trajectory modifications and its increased radioactivity suggested that whatever was responsible for the orbital changes was also generating the radio transmissions. This correlation implied that both phenomena were being produced by the same systems or processes within the object. By late April 2024, the interstellar visitor had transformed from an apparently passive chunk of space debris into something that exhibited controlled motion, sophisticated propulsion capabilities, and complex communication systems. The object's new orbit ensured that these capabilities would be on display in the inner solar system for the foreseeable future, making long-term concealment of its anomalous nature increasingly difficult. Military satellites began adjusting their observation schedules to maintain continuous coverage of the object's position and activity. The United States Space Force's Space Surveillance Network, designed to track potential threats to critical space infrastructure, designated the interstellar visitor as a priority surveillance target, requiring constant monitoring. Similar surveillance efforts were implemented by space agencies and military organizations around the world. The object had become the most closely watched entity in the solar system, monitored by every available sensor and tracking system on a continuous basis. This intensive surveillance revealed that the object was not merely exhibiting anomalous behavior, it was actively adapting its behavior in response to human attention and monitoring efforts. The dance between observation and response had begun in earnest, and humanity was about to discover what happens when the subject of scientific investigation demonstrates capabilities that exceed our understanding of what should be possible in the cosmos. The interstellar visitor had achieved something unprecedented. It had transformed itself from a passive object of study into an active participant in humanity's attempts to understand its nature and intentions. The question was no longer what the object was doing, but what it was preparing to do next. Throughout human history, certain discoveries have possessed the power to fundamentally alter our understanding of reality itself. The realization that Earth orbits the Sun challenged humanity's perception of its place in the cosmos. The discovery of evolution transformed our understanding of life's origins and development. The splitting of the atom revealed forces that could either power civilization or destroy it entirely. Each of these revelations required decades or centuries for human societies to fully integrate their implications. They challenged religious beliefs, disrupted established social orders, and forced entire civilizations to reconstruct their most fundamental assumptions about the nature of existence. The interstellar visitor represents a discovery of similar magnitude, but compressed into a time frame measured in months rather than centuries. Understanding why space agencies and government institutions have chosen to restrict information about the object's anomalous behavior requires examining the broader context of how human civilizations respond to paradigm-shifting discoveries, particularly those that suggest we are not alone in the universe. The theoretical framework for this analysis was established in 1968 by the Brookings Institution's report to NASA on the implications of space exploration for human societies. The report examined historical precedents for how civilizations respond to contact with more technologically advanced cultures, drawing parallels between European colonization of the Americas and potential extraterrestrial contact scenarios. The historical precedents were sobering. In virtually every documented case of contact between technologically disparate civilizations, the less advanced society experienced profound disruption to its social structures, belief systems, and cultural identity. The Brookings report concluded that contact with extraterrestrial intelligence could pose comparable challenges to human civilization as a whole. But the report also identified a more subtle concern. The mere knowledge that more advanced intelligence exists in the universe could trigger social and psychological disruption even without direct contact. This concern reflects what psychologists call cosmic perspective anxiety, the psychological stress that results from confronting the vastness of the universe and humanity's insignificant place within it. Studies of individuals who experience profound cosmic perspective shifts, such as astronauts who view Earth from space, document both positive and negative psychological effects that can persist for years after the initial experience. Extrapolating these individual responses to entire populations suggests that widespread awareness of extraterrestrial intelligence could trigger mass psychological and social disruption on a scale unprecedented in human history. Dr. Michael Michaud, who served as Deputy Director of the State Department's Office of Advanced Technology during the development of US policy regarding potential extraterrestrial contact, has written extensively about the societal implications of such discoveries. His analysis suggests that even technologically superior human societies would face significant challenges in maintaining social stability following confirmation of extraterrestrial intelligence. These challenges would be magnified for societies that lack the scientific and technological sophistication to understand the implications of such contact. The potential for social unrest, economic disruption, and political instability could affect billions of people worldwide. The interstellar visitor presents an additional complication. Its behavior suggests not just the existence of extraterrestrial intelligence, but intelligence that possesses capabilities far exceeding human technological achievements. The object's ability to modify its trajectory without detectable propulsion signatures indicates mastery of physics that humanity has not yet achieved. Its capacity to generate coherent radio transmissions with sophisticated information encoding suggests communication technologies that surpass our most advanced systems. Its apparent responsiveness to human observation activities implies monitoring capabilities that exceed our understanding of how such surveillance might be conducted across interplanetary distances. These capabilities place the intelligence responsible for the interstellar visitor's behavior in a category that strategic analysts call overwhelmingly superior technology. Technological advancement so far beyond human capabilities that it would be indistinguishable from what previous generations might have called supernatural phenomena. Contact with overwhelmingly superior technology presents unique challenges that extend beyond the social and psychological disruption associated with peer-level extraterrestrial contact. Dr. Jared Diamond, author of Guns, Germs and Steel, has analysed the historical outcomes when human societies with vastly different technological capabilities encounter each other. His research documents consistent patterns. The technologically superior society typically gains decisive advantages in resource control, territorial dominance, and cultural influence, often leading to the absorption or elimination of the less advanced society. Applying this analysis to potential extraterrestrial contact scenarios suggests that humanity's response to the interstellar visitor might be its most consequential decision in recorded history. If the object represents reconnaissance or first contact by an extraterrestrial civilization with overwhelmingly superior technology, humanity's response could determine whether our species maintains its independence, becomes subordinate to extraterrestrial control, or faces existential threats that exceed our capacity to address. This strategic context helps explain why information about the interstellar visitor's anomalous behavior has been restricted to small groups of highly cleared analysts and decision-makers. The number of individuals with comprehensive knowledge of the object's capabilities is estimated to be fewer than 200 people worldwide, distributed across space agencies, military organizations, and intelligence services in allied nations. This restricted group, sometimes referred to within classified circles as the Cosmic Intelligence Assessment Team, includes experts in orbital mechanics, signal analysis, technological assessment, and strategic planning. Their mandate involves not just understanding the interstellar visitor's capabilities, but developing response strategies that protect human interests, while avoiding actions that might be interpreted as hostile by whatever intelligence controls the object. The team's preliminary assessments, based on analysis of the restricted observational data, suggest several possible explanations for the interstellar visitor's behavior. The first possibility is that the object represents an automated probe designed to assess the technological capabilities of emerging civilizations. Such probes might be deployed by advanced extraterrestrial civilizations as early warning systems to identify species that are approaching technological maturity and might pose future challenges or opportunities. This hypothesis is supported by the object's apparent responsiveness to human observation activities. If the probe is designed to assess human technological capabilities, it would logically respond to our most sophisticated detection and analysis systems to gauge the extent of our scientific and technological development. The trajectory modifications that brought the object into a stable solar system orbit would serve to extend the assessment period, allowing the probe to conduct long-term observation of human activities and technological progress. The second possibility is that the object represents a communication relay designed to establish contact with humanity once our species demonstrates sufficient technological sophistication to detect and analyze its transmissions. This hypothesis is supported by the increasingly complex radio emissions that the object has been generating since its orbital modifications. The signals show characteristics of information encoding and error correction that suggest they contain structured data intended for analysis by technologically capable recipients. Under this scenario, the object might be waiting for humanity to demonstrate the ability to decode and respond to its transmissions before initiating more direct forms of communication. The third and most concerning possibility is that the object represents advanced surveillance technology deployed to monitor human activities in preparation for more direct intervention by extraterrestrial intelligence. This hypothesis is supported by the object's positioning in an orbit that provides optimal observation opportunities for Earth-based activities. The trajectory ensures regular, close approaches that would allow detailed monitoring of human technological, military, and social development. The sophisticated signal processing capabilities demonstrated by the object suggests that it possesses the ability to intercept and analyze human communications, radar transmissions, and other electromagnetic signatures that reveal detailed information about our technological capabilities and strategic vulnerabilities. Each of these possibilities carries profound implications for humanity's future, but they share a common element. They all suggest that our species is being evaluated by intelligence with capabilities far exceeding our own. The evaluation process appears to be ongoing, with the interstellar visitor continuing to gather information about human activities while gradually revealing more of its own capabilities through increasingly sophisticated transmissions and precise orbital adjustments. This gradual revelation suggests a carefully managed contact scenario designed to allow humanity time to adjust to the reality of extraterrestrial intelligence, while providing opportunities for the extraterrestrial intelligence to assess human responses to their presence. However, the success of this managed contact scenario depends critically on how human institutions and populations respond to the knowledge that we are being observed and evaluated by non-human intelligence. The decision to restrict information about the interstellar visitor reflects concerns that premature or uncontrolled disclosure could trigger responses that might be interpreted negatively by whatever intelligence controls the object. Panic, aggressive military responses, or attempts to interfere with the object's activities could be perceived as hostile actions that justify more direct intervention by extraterrestrial forces. Conversely, measured and thoughtful responses that demonstrate human wisdom, scientific curiosity, and peaceful intentions might lead to more beneficial forms of contact and interaction. The restricted analysis teams are reportedly developing graduated disclosure scenarios that would gradually introduce the public to the reality of the interstellar visitor's anomalous behavior while preparing appropriate response strategies. These scenarios include protocols for scientific collaboration, diplomatic outreach, and coordinated international responses that would present humanity as a unified and peaceful species worthy of positive interaction with more advanced civilizations. However, the implementation of such scenarios faces significant challenges. The interstellar visitor's activities are becoming increasingly difficult to conceal as its radio transmissions strengthen, and its orbital position brings it into range of amateur astronomical observations. Independent researchers around the world are beginning to detect and analyze the object's emissions, using equipment that is becoming increasingly sophisticated and widely available. The democratization of astronomical observation technology means that the window for controlled disclosure is rapidly closing. Moreover, the object itself appears to be actively working to reveal its presence to humanity. The increasing strength and complexity of its radio transmissions suggest that it wants to be detected and analyzed by human observers. The precision of its orbital modifications indicates that it has positioned itself for optimal observation by Earth-based telescopes and monitoring systems. These actions suggest that whatever intelligence controls the object believes that humanity is ready for more direct awareness of its presence. This creates a potential conflict between human institutional desires to control the pace and nature of disclosure and extraterrestrial intentions to reveal their presence according to their own timeline. The resolution of this conflict may determine not just how humanity learns about the existence of extraterrestrial intelligence, but how that intelligence chooses to interact with our species going forward. Recent analysis of the object's radio transmissions has revealed mathematical sequences and physical constants that appear to be designed as universal communication protocols. These transmissions include prime number sequences, the mathematical relationship pi, and the fine structure constant that governs electromagnetic interactions. Such mathematical constants would be recognizable to any technologically advanced civilization and represent logical starting points for establishing communication between species with different languages and cultural backgrounds. The inclusion of these constants in the object's transmissions suggests that it is actively attempting to initiate formal communication with humanity, rather than simply conducting passive observation. This development has prompted urgent discussions within the restricted analysis teams about how to respond to these apparent communication attempts. The response strategies under consideration range from passive monitoring and analysis to active attempts to reply using Earth-based radio transmissions directed toward the object. However, any response carries significant risks and implications that extend far beyond scientific curiosity. Once humanity responds to extraterrestrial communication, we will have definitively announced our presence and capabilities to intelligence that may be monitoring our activities throughout the solar system and beyond. This announcement cannot be retracted or reversed, and its consequences may affect every human being alive today and all future generations of our species. The decision about whether and how to respond may be the most important choice that humanity has ever faced. Yet this decision is currently being made by a small group of individuals operating under extreme secrecy, without input from the broader scientific community, elected representatives, or the global population that will be affected by the consequences. The democratic deficit in this decision-making process reflects the practical challenges of managing information with such extraordinary implications, but it also raises fundamental questions about who has the right to make choices that will determine humanity's relationship with intelligence that may be far more powerful than our own. As the interstellar visitor continues its patient orbit through the solar system, transmitting its mathematical messages and demonstrating its technological superiority, these questions become increasingly urgent. The object appears to be waiting for humanity to demonstrate the wisdom and maturity necessary for productive contact with more advanced civilizations. Whether we can meet this challenge may determine not just our future as a species, but whether we deserve to have a future among the intelligent civilizations that populate the cosmos. The interstellar visitor deleted the comfortable illusion that humanity was alone in the universe, but it replaced that illusion with a reality far more complex and challenging than our species has ever had to confront. The question is no longer whether we are alone. The question is whether we are ready to join a community of intelligence that extends far beyond the boundaries of our small world, and whether we possess the wisdom to navigate the opportunities and responsibilities that such membership would entail. Tonight, as you look up at the stars, remember that something up there is looking back, something that has travelled between those stars to reach our solar system, something that has demonstrated capabilities we can barely comprehend and intentions we are only beginning to understand. The universe is far stranger and more populated than we ever imagined, and humanity's greatest adventure is just beginning.